So I'm going to talk to you about filament plots for data visualization. So to begin with, let's talk about kind of standard data visualization procedures and what kind of failings do they have. Our standard 2D scatter plots are inherently lossy. If you have higher dimensional data, you're necessarily losing some sort of information. The kind of information that you lose is that, well, 2D scatter plots are good at problems where if points are really close together in the data space, then they can be close together in the visualization space, right? But the problem is, if they're close together in the visualization space, that doesn't mean that they were close together in the data space, right? When you project down, even in a nonlinear way, you're always going to distort those kind of distances, right? Really long distances can still be potentially collapsed. Nevertheless, 2D scatter plots are incredibly useful. You use them all the time for data visualization. They can tell us really important and intuitive information about data sets, and that's why we see them everywhere. Of course, there are nonlinear methods, and they manage to mitigate certain distortion properties, and in particular, they're very good for depicting cluster structures that might emerge in high dimensional data sets. So of course, the standard methods are multi-dimensional scaling, stochastic neighborhood embedding, and more recently, the UMAP method. On the other hand, nonlinear methods will always involve more computation. UMAP is still pretty efficient, but there is some computational overhead, especially if you have a number of points. In really high dimension, this could be an issue. So you can construct algorithms that try to do the best in the lossy scenario. However, you can just avoid that entirely by saying, well, I'm going to construct a visualization that's completely lossless. And in fact, we've had these for a number of years. For example, a matrix of scatter plots, or what's called the draftsman plot by Tukey, right? So the matrix of scatter plots, basically it'll take every pair of variables in your data set, say a pair of columns if you believe your data is in rows, and it will create a scatter plot from that pair, typically after standardization or some sort of standardization. So here's the idea for the iris data set. Here you have the 3 species of iris, and here you have a 4-dimensional data set where the dimensions are sepal length, sepal width, petal width, and you can see all the different scatter plots. And you see how that's actually pretty informative. And for 4-dimensional data, and even up to 10-dimensional data, a matrix of scatter plots is really great. I would use that all the time. Nevertheless, there are certain failings. The first failing that you get is that if I have a point in one of these scatter plots that corresponds to a data point, how do I know that it corresponds to another point in another scatter plot, right? Somehow there's not contiguity between the points in the different scatter plots, so you can't say, oh, this point and this point are common. So somehow you split the data across. Also, as you go into higher and higher dimension, right? Well, you have a lot of scatter plots, right? You have dimension choose 2 scatter plots, and they're displayed over the entire viewing plane. And so in, say, even 100 dimensions, you have way too many little scatter plots to look at. You could zoom around, right? You can always do something interactive, right? But the interaction is fairly complicated. And in some sense, the kind of visual entropy, in air quotes and scare quotes, the visual entropy of every single data point gets higher and higher, because for every single chunk of that image where you have a scatter plot, you have one piece of information, or kind of 2 pieces of information about a single data point. And so your information about an entire data point is smeared across the image. And so in high dimension, a matrix of scatter plots will not really do the job that you want it to do, right? You can't connect the dots very easily. So I've summarized this, but here's the upshot of that. So the problem is kind of general for what are called small multiples plots, right? So if you have a data visualization, right, a particular data visualization that has many different facets, right? Well, you can always plot a bunch of data visualizations in one frame and look at them, right? And that's called a small multiples plot, where you have small multiples of different visualizations or different facets of a particular visualization being displayed for you, right? But as soon as you get past a 10 by 10 grid or larger, right, there's just kind of too much information in a small multiples plot. The next thing is parallel coordinates or parallel plots. So this is, when I saw this, I thought this was the silliest thing ever, but it's actually not so bad. The idea is that you're essentially embedding your data into a space of piecewise linear functions, right? These very simple splines. You have one knot for every single dimension. And then you simply say the value at that knot is the value of the data point at that dimension or coordinate. And actually, you can see this is a reasonable plot. You can see the separation of some of these classes. But again, this is for 4-dimensional data, right? In higher dimension, you have something incredibly noisy, right? And in particular, there's not necessarily a guarantee that you don't have really high frequency content to the different linear splines that you're displaying. And so visually, the things that you're looking at are not pleasant. They're very jagged and potentially highly noisy. But also, you're displaying 1D functions in 2D. Right, and so you have a curve in 2D. Well, you're going to have a lot of crossings. And a lot of crossings lead to a bunch of clutter, right? If you have crossing over crossing over crossing, then you can't really see a particular plot, right? And in this data set, there's not so many points, right? But as you get more and more points, this clutter can really be, occlusive. And so another word that I use for this is legibility, right? If you have these too many points, then you have kind of too much visual entropy, and the legibility for these simultaneous plots of points goes down, right? That's another nice thing about this, is that you can plot everything simultaneously. Whereas with the small multiples plots, you could only display maybe 100 things at a time reasonably. But here you can kind of compare everything all at once visually, just like you would in a standard 2D scatter plot. That's the nice thing about it, right? You plot everything simultaneously. You get to look at how the relationships between all the points. The next plot is Andrews plots. There should not be an apostrophe there, actually. It's just Andrews plots. So these plots were due to Andrews, and they're quite simple. Basically, you map instead to these piecewise splines, you map to a trigonometric polynomial, and it's a linear map to the coordinates of that trigonometric polynomial. So the simplest one is, well, you have a map from RD into L2 that's given by an even better space than L2, of course, right? Phi of x evaluated at a time point t, where t is from 0 to 1, is going to be simply x1, the first coordinate, plus x2 times this first member of a real Fourier basis, plus x3 times the third member of the Fourier basis, so on and so forth. So I just increase the frequencies, right? And so for the 4-dimensional data that we've been looking at, the map would just be this. So this is an old method. This is a very simple method introduced by Andrews. And he was a statistician, and he was interested in kind of the variability of these and basically estimating variance of these functions. It's very similar to parallel plots, but suddenly the functions are a little bit nicer to look at. Individually, they're nicer to look at, right? They're somehow not as noisy. And why are they not noisy? Well, you're forcing the system to have lower frequencies, right? And so there's less visual noise. Aesthetically, it's a slightly nicer just to look at. One thing that Andrews did not note, one thing that Andrews did note, right, is that, well, this is actually a linear isometry from RD into L201. So this map will take data and preserve distances, but now in an L2 sense, right? Well, the L2 distance between functions, if you are a hardcore electrical engineer, you might be able to look at two functions and be able to visualize, their kind of energy difference. Or maybe you have an intuition for that. I do not. The L2 distance is actually kind of weird, right? The distances that make sense in functionally and visually are L1, right? It's just the area, the net area between those two curves, right? And L infinity is the biggest gap between those two curves, right? But here's the nice thing, right? Is that, well, if you have a linear isometry, well, L1 and L infinity sandwich L2. And so that means that somehow you can do kind of comparisons, visual comparisons, and they are sensible. They have some sort of like sensible content in the original dataset, right, in the data space. And so you can say visually, oh, these things are close together in L infinity, therefore they have to be close in data space. Or these things are far apart in L1 visually, you can say that, and therefore they have to be far apart in data space, right? And that's very different from what we had with scatterplots, right? In particular, we didn't have that lower bound with scatterplots. And so now we can do a visual assessment of things. That's the nice thing about having this linear isometry. One thing to note is that actually, you also have kind of a, you can say you have a linear isometry here, right, for the parallel plots as well. And so you can get similar kind of properties or similar kind of metric comparison properties. But we're still mapping 1D functions to 2D. And so you can see that there's a ton of clutter. Everything is living on top of each other. And especially when you go from just raw coefficients to standardized coefficients, and then instead of using just the raw embedding, use PCA scores to construct your Andrews plot, things get a little squiggly, right, in scare quotes. Professor Casey.
Had anybody thought of, after seeing the Andrews plots, to going back to approximating by linear splines with approximating by, say, order K B-splines?
Oh yes, so actually that is true. So I believe one of the standard things you can do with Andrews plots is you fit a cubic spline instead, right?
All right.
And
the infamous thing, cubics is sort of optimally computational.
And especially since it's, I would say it's more used in the statistics world. They're very happy to use cubic splines for anything, right? So that definitely is true. So in some sense, I'm underselling parallel plots here. They can be smoothed out, right? And in fact, you can also, there are some methods for organizing the coordinates so that the frequency, right, the frequencies represented by the parallel plot or the parallel coordinates are not so terrible to look at. So you can do a number of things to ameliorate these plots.
Excellent. Thank you very much.
Yeah, I don't want to undersell them. But nevertheless, you still are in this situation where you're plotting a bunch of 1D curves over 2D curves, which is, not the best thing you could do. So here's an idea. Instead of doing 1D curves or 1D functions in 2D, we're going to do 2D functions, right? That functions from one variable to two variable, right? and then we will plot them in 3 dimensions, right? The idea is that if I have a curve now in 3 dimensions and another curve, only rarely will they ever intersect. And so somehow we remove ourselves from this clutter. Of course, we're only taking 2D projections of these things. But drag to rotate and drag to zoom and pinch to zoom interfaces are very standard now. And so you can explore this data set very simply in 3D by simply moving it around, zooming in and out, right? So it is more of an interactive plot, but with standard human-computer interactions. What you'll say is that, well, your goal is to get something a little nicer, and these plots, while they're interesting, they have this weird braiding that makes for a lot of visual clutter, right? They're kind of like really braided together and windy. And so visually, you would say that this is actually really complicated. And so for the price of solving a matrix differential equation using these functions as data, right, we can actually create a bushier plot that has kind of more nice visual separation, but still has nice smooth aesthetics. And so let me go ahead and share the interactive plot so you can see. And so here's the data. So you can drag to rotate. You can see the different classes and how nicely they separate. But also you can view the boundary of, say, the versicolor and virginica, where there are some ambiguous points, right? Points that kind of seemingly bleed into each other. And of course, you can zoom in and zoom out as you like. But these are standard. My only suggestion is don't go here on mobile. It just crashes on your mobile device. But if you go to this website on your desktop, it's nice to look at. And when we get later into the talk, I'll show you some other examples for some other standard data sets that are higher dimensional and slightly more interesting than this data set. Not only are we going to construct these things, but we're going to construct them in an optimal way. So we can actually prove that these plots that we create are optimal in a suitable sense. And then there are other desirable features that we would really like to have. And we show that, that asymptotically, we can make some other desirable features appear, asymptotically in the dimension of the data. So here's the summary. That was a really quick summary, but let me give you a slightly more technical summary. So we're going to let H, math calligraphy H, be H101. It's the Sobolev space of L2 curves with L2 derivatives.
Nate, are you back to your presentation, or are we still looking at the...
Oh, sorry. Yes. Okay, so we're going to let mathcal H denote the Sobolev space of L2 curves with L2 derivatives. Given a data matrix X, we parameterize linear isometries phi from RD into H2. That is, I take a data point in the data space RD, and I spit out a pair of functions in a linear way. And also so that I am an isometry. And I'm going to parameterize the set of linear isometries from RD into H2 that produce, on average, optimally smooth curves over the data set. So you actually get a lot of these things that are optimal. And then we can say, well, is there a particular member of the parameterization that has some other desirable property? Well, the parameterization reveals many degrees of freedom And we will show that there is a particular set of parameters such that the maps x from x into phi of x evaluated at t, right? So this is now, right, when you look at this map, this is a map from RD into R2, right? All these maps are uniformly close to being projections from RD into R2. And so that means that each individual point is or each individual slice of these functions will be a nice scatter plot. That's the idea. And then we'll use these things called Bishop frames, which are slightly related to Furness-Serre frames, to promote these curves to unit length 3-dimensional curves that are bushier, right? The isometry will entail that the distances in data space, right? So we'll lose some of the metric comparison properties when we do this map, right? When we promote to these unit length 3D curves, which we'll call filaments. We'll lose some metric comparison properties, but you can still say that there's a relationship between total relative curvature and maximum relative curvature. So distances are still preserved, not in a totally visually interpretable sense, but if you look at it carefully, you can tease out these differences. The code is available on my GitHub. The paper was recently accepted to ACHA, and of course there's a preprint on archive. Okay, so our next step is to describe the optimization setup. So what are aesthetic conditions on linear isometries that are desirable for data visualization? For notation, we're going to let x be d by n. So I'm cheating again. Data will be in columns. Data is in columns. And phi is a linear map from RD into Sobolev space across the Sobolev space. So we're going to identify 4 different properties that are desirable for this phi. The first is a property that prevents global degeneracy. So to avoid collapsing graphs, we're going to enforce what we'll call an isotropic isometry condition. So that means that for any direction u in R2, when I take the L2 norm of u transpose phi applied to the data point, that's always equal to the norm in the data space. So not only is this an isometry, right, but it's actually an isometry in every single direction of the data. And what does this do? This prevents the functions or the functions you get from getting squashed down into becoming 1D functions. So you truly are filling out your 2-dimensional space. The next property is a local non-degeneracy property. Well, you can also, right, even if you are preserving L2 along all these different directions, right, well, that's global over all time. You could still have a case where at a particular time slice, you're squishing the data flat into 1D. So all the data has to live in 1D. We'd like to avoid that if possible, so that every single time slice induces something basically like a scatter plot, maybe with different dimensions coming into play. But we don't want things to just get squished down and lose information in that sense when we could be using all of 2D space. So to avoid local collapsing graphs, we try to enforce a projective Tour condition so that phi is a scaled projection matrix for all t in 0, 1. Ideally, that would be the case. Visual interpretability. We would also like to ensure unbiased, visually accessible interpretations of these L1 and L infinity bounds. And so we'll require that phi maps, instead of to curves themselves, phi will map to derivatives of periodic curves. And so this will this will kind of help us understand what's going on, because visually, if we do this and we're mapping to derivatives, then in the L1 sense, that's the integral over the velocity, right? Right. If I'm mapping to periodic curves, L1 is simply the speed, right? The integral over speed, or the total kind of distance traveled by the by something moving along the curve. And L infinity bounds on the derivative are saying that points kind of close by should kind of flock together, right? When they move in 2D, they move together ideally. So we'll force phi to map to these derivatives. The next thing is that I want to preserve a smoothness condition, right? Or I want to have some sort of smoothness to the plots, just so that we avoid things like these problems with the naive implementation of parallel plots. So we'll introduce this thing called the minimum mean quadratic variation. So this will be a program, and it's going to try to minimize this mean quadratic variation, or MQV function, of the map phi given data x. And it's simply the average norm square of the tangent function of phi applied to a data point xn. So let's unpack all of these a little bit more. So isotropic isometry defeats global degeneracy. So if you just have isometry, right? If phi just is an isometry, well, it could degenerate into something like this, right? Where you simply map phi in the second coordinate to 0, and then you have some sort of standard 1D Andrews plot, right? So this would be permissible if you just had an isometry condition, but then there's no point in really looking in 3 dimensions, right? The curves will all be stuck on a single plane, so it's useless. So this is maybe the most important condition that you could try to impose on your system so that you can do actual real visualizations in 3 dimensions. The next is the projective tour property. So consider the bad thing that could be happening if you don't have a 2D slice or a 2D projection at every single time sliced. Let's consider the extreme case where the rank of phi of t, right, as a map from RD into R2 is always 1. Well, then there would exist a phi in H2 such that the norm of phi is 1 for all t, and for all x there is a gamma x in H satisfying phi of x of t would be gamma x of t phi of t. So essentially, all you would be allowed to do is you would have a particular function that you map to, and then you would be able to use a scalar multiplier times that function, right? So your directions would always be the same, and you would just have a different multiplier. But if you enforce the rank 2 condition on phi of t, right, that means that at every single time slice, you have kind of 2 degrees of freedom that you can take on, right? So that is, you have phi 1 of t and you have phi 2 of t at that time slice. And therefore, phi x of t could be any linear combination of these guys, right? Whereas if I just had phi of t, they would have to live along one particular direction. That's it. The next thing is visual interpretation. So we're going to map to derivatives of curves. And so if we let gamma prime of x be phi of x and gamma prime of phi of y be derivatives, then we have the following kind of metric comparison bounds, right? So the integral from 0 to 1, norm gamma prime of t x, gamma y prime of t dt is a lower bound for the distance in the data space, and the soup over the differences between the tangents of these different curves is an upper bound for the distance in the data space. And this can be interpreted now. This is the length of the difference curve, right? So this is the length of the difference, right? Whereas this is kind of the maximum velocity, the difference of the maximum velocities between two curves, right? So visually, you might be able to pick those out, and especially if you kind of relativize the graph, right? So you just subtract one plot from another, or you pick a particular plot and you subtract it from all the others, then you could see the differences very clearly. So here are the main results. First, to state the main results, it helps to have a different representation of linear maps from RD into H2. Well, omega will be such a linear map if and only if there is a phi in a 2 by D matrix of H functions, right? So it's a 2 by D matrix where each entry is a function from the Sobolev space, such that phi x evaluated at t is simply phi of t times x for all x and almost all t, of course. So this is simple enough to prove, but it's useful to think about it in terms of what's happening at every single time slice. So for phi in this 2 by D matrix of Sobolev functions, we will abuse notation and we'll write just phi of x to denote the linear transformation of x in RD to H2. So here's a picture of what this kind of means, right? So if you have phi in H2, we'll call phi j dot transpose, right? These are things in HD. There are two of them, right? Oh, this is now 2 by D, 2 by D, 2 by D. Yeah, 2 by D. So they're not two of them, right? But we're going to call these functions the component slices of phi. And we'll call the 2 by D matrices phi of t, the time slices of phi. And we'll call the functions phi dot k, right? These there are two of, right? In H2, the coordinate slices of phi. And so here's the map, right? So in time slices, of course, you have 0 to t. The component slices, you always have two of them. And then you have coordinate slices for each dimension of the data. So the coordinates correspond to the data dimension. And this just illustrates the values, right? This is a false plot to just illustrate the values that you would take, right? So the relative value of this curve would be taken on this time slice. So this would populate a 2 by 3 matrix, right? So in this case, little d is equal to 3. So we can transfer all of our aesthetic conditions to conditions on this matrix of functions, right? So the isotropic isometry conditions becomes the L2 quadratic constraints, which are, well, if I integrate from 0 to 1, right? If I take inner products of jk versus j prime, k prime, phi, well, I get a delta function, or a Kronecker delta. The projective tour condition becomes the quadratic constraints. Well, if I take the inner product of j with j prime, the row j with the row j prime, well, that gives me d times a delta function, right? I have to do some scaling because I did the isotropic isometry condition here, so some scaling had to happen. But this happens for all j and j prime in the 2 set, right? Consisting of just the points 1 and 2, and all t in the interval 0, 1. And finally, being the derivative of a periodic function condition, that's going to be encoded by just linear constraints. Phi jk is equal to 0, of 0 is equal to phi jk 1. And then the integral of the different functions will all be 0. So that's sufficient to specify all the constraints that we want, all the aesthetic constraints. And so we can set up this quadratic minimum mean quadratic variation program, right? It's seemingly simple, right? I just have basically, an infinite dimensional optimization problem, right? It's a quadratic optimization program with quadratic constraints and infinite dimension, seemingly doable, right? But it turns out it's quite difficult. You don't want to do it. So instead, we're going to do something that we can actually approach. We're going to drop one of the conditions and just see what happens when we drop that condition. And the thing that we drop is the projective tour condition. Because if we drop the projective tour condition, suddenly we can attack this with reasonable methods. And that's it. So this will be our program that we try to solve initially. So here's the theorem that you can say. We'll let x have this singular value decomposition. So x is equal to u sigma v transpose, standard singular value decomposition, where u is this system of columns, u1 through ud. Then phi, right, the linear map phi will solve this partial minimum mean quadratic variation program if and only if there exist unimodular constants, right, that is complex numbers with complex modulus equal to 1, and a sequence of signs such that phi x of t exactly gets mapped to a trigonometric polynomial of this form, right? The coefficients of the trigonometric polynomial have to be inner products of the UK's transposed with x's, right? Inner products of UK with x, the data. I'm allowed to spin using these unimodular constants. And then I have to multiply by some trigonometric polynomial component, where I also get to choose the sign, right? This can either be -1 or 1. I get to choose that. And you'll notice that this is complex, but I'm getting a map to R2 by just identifying R2 with C in the standard code. Right, so this is what the map will look like in the optimal case, right? And what you identify this with is, well, these are PCA scores, right? These are coefficients along the PCA basis for the data set. And then the degrees of freedom that I get are exactly from these WKs, right? For every single dimension, I have 1 degree of freedom, right? I can exactly spin things. So that's a little bit weird, right? That degree of freedom is a little hard to visualize, right? But what does it mean, right? What would it mean to keep everything fixed, right? You fixed your WKs, you have your UKs fixed, and you just spin each WK, right? Well, it means that that particular component of frequency, right, or that particular contribution, it really actually just gets it just gets kind of like spiraled in a corkscrew. You just rotate that a little bit, right? And so you can visualize this kind of in 1D, right? What happens in 1D when you kind of mix sines and cosines, right? Well, if it's sines and cosines of a particular frequency, all that corresponds to is kind of the translation invariant subspace, which consists of linear combinations of that sine and cosine. And so it's like you're moving just that component, that frequency component, by some amount in this regard. But it's still confusing. Is there a way to reduce that, or to pick something that's maybe a little bit more useful? So here's an example of the iris data set of this map where the omega k's are just 1. Simple enough. I'll zip through because I'm running out of time. But the proof sketch is you basically use a vector value discrete time Fourier transform to diagonalize the differential operator involved in the mean quadratic variation. You can get a lower bound on the mean quadratic variation function by truncating the diagonal after this Fourier transform, right? And then you can use Fisher-Courant to ensure that the minimizers of the truncated problem match high variability directions in the data with low frequency components. Yeah, so that's another important point, right? Is that we're going to, right, if this is the singular value decomposition, I'm matching high variability directions of the data with low frequency components of the functions, right? So if I have a really high variability thing, it really wants to go to the lowest frequency possible under this mapping. Okay, so there is one way that I've found where you can pick the omega k's so that you get yet another nice thing happening, right? So the idea is that you're going to use these omega k's, which are quadratic phase shifts, right? So omega k is going to be e to the 2 pi I k squared over 4t. And wk is just equal to 1. Well, if you choose these omega k's, you will also have that if you scale your time slices appropriately, the singular values are in this interval, square root 1 minus something that's big O of square root t, 1 over square root t, right? And so in particular, as if d is really large, then your singular values are very close to just being 1, right? And of course, you only have 2 singular values for each time slice, right? Each time slice is a projection from RD into R2. And so that means that you can at least get an asymptotic local non-degeneracy behavior, right? You don't get the hard constraint, but asymptotically you get this. And so this is a nice condition, and we can prove it using some nice bounds on Gaussian sums. So here's the idea with the iris data set. We can compare what happens with this kind of naive Andrews plot embedding with the embedding, but where I use quadratic phase shifts for my omega case. And you can see that, right, what's the difference between the singular values of these time slice maps for these functions, right? Well, we see that for this blue curve, which is the difference of singular values, or the singular value gap for the naive embedding, well, at certain points, it just crashes, right? It crashes to the largest possible gap, right? Which means that one of the singular values was 0, which means that at some points it gets squished. And in fact, portions along this entire section will tend to squish the data towards a one-dimensional plane. But I see that if I use the quadratic phase shifts, yeah, there's some variability, it's a little wiggly, but generally the gap is relatively small. There's some constraint on the gap. So this is the idea, is that you have to invoke uniform bounds on these generalized quadratic Gaussian sums that are available in this paper by Paris. There he does this asymptotic expansion, and he bounds this error term. So really the hard work was done for me. I just had to find his paper and figure out what it all meant. So discussion, right? So the proof of theorem 1, you can actually reconfigure it to show that 1D Andrews plots using PCA scores optimize the mean quadratic variation. So in the original 1972 paper by Andrews, he said, oh, you could use these, but there was no reason why. It just seemed like a good idea, right? Seems reasonable enough, right? This work actually shows in some way that, well, one thing it does when you do that is that it produces a map that optimizes this mean quadratic variation. We have this L1, L2, L infinity bounds, right? Things are bound, but the gap is large, right? It's on the order of square root of the dimension. And so these bounds, right, we want these bounds to be visually interpretable, but in higher dimension, they actually kind of fall apart, right? The L2 distance, of course, is still preserving things, but the L2 distance is not visually intuitive. At least not for me. At least not for me. Maybe you talk to electrical engineers who look at two functions and they can just spit the L2 distance off from their head. I would love to have that skill. I do not. Finally, using Johnson-Lindenstrauss, a data set of size n may be embedded in log n dimensions with small distortion. And so you could actually squeeze this gap a little bit better, right? But you then have a slightly lossy procedure, right? But if your only interest is to do, high fidelity metric comparisons, then you could first dump things to a smaller space and then do this embedding if you wanted to do that. Okay, so I'm going to zip through. I don't have much time, but basically, you can take these optimal Andrews plots, and then you can promote them to these bushier plots that seemingly separate classes a little bit better, but also still in a lossless way. So what we do is we're going to do a nonlinear embedding of functions from this H2 space, and then we'll get a slightly nicer visualization that way. And the idea is to use moving frames. So the standard moving frame is, of course, I have a curve and I get the tangent, I get the normal, what kind of the direction where the tangent is heading locally, and then the binormal, which is just the cross product of the two. That's the standard one. And you can solve them using these Frenet. You can solve for them using these Frenet-Serre equations. And you'll notice that you need two functions there, the curvature and the torsion, to do this. And so that suggests that we can do something similar. What we actually use are what are called Bishop frames. They're related to Frenet-Serre frames, but they're actually a little bit nicer in the sense that you don't need a third derivative, and you can define them for many more curves than the Frenet-Serre system. And you can also tease out the curvature and torsion from these when the torsion exists, of course. So basically, we just integrate this, and here's the map, right? So we're going to define a nonlinear map from C1 squared to C1 cubed, right? So from 2D C1 functions to 3D C1 functions. So that gamma of phi is equal to 0. That should be gamma phi of t is 0. Gamma phi of 0 is 0. And the derivative of this embedding is the first row of the solution to this matrix initial value problem. So I set up the Bishop frame, I solve for t, and then I integrate it, subject to the fact that it starts off at 0. And the initial condition is simply that the frame is initially just the identity matrix. And so given a 3D Andrews plot map phi from these theorems that we've displayed, the filament plot will simply be gamma of phi of x. So I won't go through all the consequences of it, but there are some things that you can say, right? The properties of the optimal 3D Andrews plot do say something about the relationship between curvature and torsion of this map. But in general, it's going to be a little bit different. Computation is actually pretty efficient. You can use what's called a Lee-Runge-Kutta method to solve these systems pretty efficiently. The last thing, I won't be able to talk about hyperframes. I'm out of time. But this problem, has some sort of like finite frame theory formulation in some sense. And so these things called hyperframes show up, which are kind of mixtures of fusion frames and superframes. And I guess I'd really like to show you, we don't have much time, but I'd like to show you some of these other data sets. So this was, of course, Iris. And if you go to the website, you can see this, and you can download the code and see some, one more visualization. So this is the Boston housing data set. And so, this is like 13-dimensional data where, they study different aspects of statistical areas in Boston in like the 60s, I believe. And here the plot is colored by decile of median housing price for that statistical area. So you can explore your data that way and find outliers and things like that. Here, this is the Wisconsin breast cancer data set. Here, this data is like 30-dimensional. And their scores of like visual information from biopsies of potentially tumor cells, and either the biopsies correspond to a malignant tumor or a benign tumor, a benign growth. And you can see some nice separation here, and you can visualize everything. But in particular, for just a little bit more work, right, you get these lossless plots. Okay, I'll call it quits here. And thank you very much, everybody, for your time.